Hi, I'm volcanologist Dr. Janine Krupner, and this is my guest.
Hi, I'm volcanologist Diana Roman.
Thank you so much for joining me for this 40th anniversary of Mount St. Helens eruption series. And you have a memory of the eruption, don't you? Could you take us through what you remember from the 1980 to 86 eruption?
Yes, I'm old enough that I do have a memory. So I was 4 in 1980, and I don't remember the beginning, but I do remember when I was 10 years old in 1986, hearing about the end of the eruption. And I think it was actually the first volcano that I ever remember hearing about in the news. So it's a special eruption to me in that sense.
And now you're working on them around the world. It's
Now I work on them from my kitchen in my living room. Yes.
so since 1980, 40 years have passed. Back in 1980, they had very early monitoring technology, very early understanding of explosive eruptions and what signals that gives us. Since then, there's been an enormous change in technology, in our understanding, in our integration of different technologies as well, that help us to understand volcanic activity and then help us help communities that live around volcanoes. So can you take us through some of the big changes that you've seen happen that help us do that?
Sure. Well, so some of the big changes have been in the instrumentation. So back in 1980, we were using seismometers to monitor volcanoes. We were using leveling equipment, surveying equipment to sense deformation, and we were using very early instruments to detect gas. Now, we still have all of those instruments, but they're a lot more sensitive. They're a lot more capable of detecting different types of signals. So that's one real way in which things have changed. And then the other thing is that we have new tools now. So arguably the biggest thing is we have the ability to monitor and study volcanoes through satellites. And this lets us look at volcanoes where we can't get to the volcano to put instruments on the ground. And we can see deformation from space. We can see increases in gas. We can see increases in temperature that tell us about what the volcano is doing, what it's likely to do next. So that's been a really incredible advance for all of us.
And it's something that we have now that they didn't have back then is the internet.
Yes.
So you mentioned that you can look at volcanoes from your kitchen. So what does that look like?
That's right. So I'm actually going to share something on my screen here. And this to me is every time I'm able to do this, I just think how incredible this is. So this is actually a real-time feed of seismic data from a seismometer that's in the crater of Mount St. Helens. And I can sit in my kitchen here in Washington, D.C. and pull up this real-time data feed of the raw seismic data and look at it. And that to me is a huge advance, and it's a huge advance for the people who need to monitor these volcanoes. So just to tell you a little bit about what you're looking at, I was a little startled when I pulled this up this morning. You see this big noisy thing at the bottom. That's actually from an earthquake, a magnitude 6.5 that happened in Nevada a few hours ago. And so the seismometer is so sensitive that even in Washington state, it sees this really clearly. So that's not related to the volcano. But then we have all these little pops in here. And my guess would be, not having really looked into it, that these are probably little volcanic earthquakes happening at St. Helens. And this is a very typical thing for the background of St. Helens. It tends to have a lot of these little tiny earthquakes just when it's in a dormant state. So it's really amazing that I can just pull it out. I can say what St. Helens doing today seismically, and I can pull this up here, and the people who are monitoring can also examine the data from home, which is obviously very important right now.
Such an incredible piece of technology, and it's pretty small too. You have a seismometer with you there.
I do. I snuck into the lab and grabbed one. So this is one of my seismometers. This is a pretty typical modern instrument. You can see how small it is. It's really heavy, but it's actually very small, which is great because we need to be able to put these in our backpacks or put them in a helicopter and take them out to the volcano. It's also incredibly sensitive compared to early seismometers, both in terms of just how tiny of a ground vibration it can detect, but also the range of frequencies. So one thing we've learned about volcanoes and the seismic signals that they produce is that the seismic signals cover a big frequency range, from like the very white, deep, low frequency things to the high pitched, higher frequency rock-breaking earthquakes. And for us, being able to see all of those frequencies is very important. So our instruments now are actually very sensitive in a wide range of frequencies compared to earlier instruments. And that's been one of those, like I mentioned, the instrument is the same, it's still a seismometer, but it does its thing in a much more sophisticated and meaningful way.
And looking at, back at the Mount St. Helens eruption, leading up to the event, we had a lot of earthquakes, there wasn't a lot of gas, but something that really stuck out was the bulge. So the actual physical deformation of the north flank of Mount St. Helens. Yes. So they were using, was it electronic distance measurements to try and bounce lasers off to see that movement changing. But our technology has vastly improved since then to measure this deformation. So can you take us through some of how that has changed?
Right, so the infamous bulge everybody knows about, and I wish I could have seen it, because apparently you could actually see it growing just with your eyes. But the way they were measuring it, it was actually surprisingly accurate, was by putting targets on it and shining EDM, electronic distance measurement, to get a sense of how fast it was growing. So today, the way we don't do EDM anymore. Generally, the way we measure deformation today is either using GPS receivers, so it's the same thing as the GPS in your car, except it's super sensitive, and we can track points on the ground and see how far they're moving over time. Or we have satellites, and we have amazing satellites satellite instruments called synthetic aperture radars that basically take a snapshot from space and then take another snapshot a little later, and by looking at the difference in those snapshots, we can actually visualize ground deformation down to millimeters. So that has been incredible in terms of the technology and also the ease of it, just being able to leave the instrument out or download the data from the satellite versus having to go out and make that measurement every day, often in very dangerous circumstances like at Mount St. Helens in 1980.
Yes, I can only imagine what the community how we'd be reacting today if we saw a bulge like that. I mean, hopefully there'd be no people around in the way, but it would be shocking, I think, to actually witness that.
It must have been, and one of the things that we now understand that relates back to that bulge is the ability of volcanoes to erupt sideways, and that bulge may or may not have been telling that this was going to be a lateral blast. But I think, one thing that in terms of the idea side and how things have changed since then is we're much more aware of now looking at the deposits of around other volcanoes, that they don't necessarily always go up, they can go sideways. And that's a very important thing to keep in mind when monitoring and trying to keep people safe.
And something we can do now, especially with the enormous technology power that we have and computing power, is we can integrate these different styles of monitoring. So we can look at the deformation and the seismicity, and we can look at the actual rocks, not quite in real time because it takes a bit of time to prepare them and analyze them. But your group there does quite a bit of looking at different data sets and integrating those, right?
Right. So, I mean, I'm a research scientist, and we're always trying to pull in different pieces of information to understand a particular eruption or a particular volcano. But it's also really critical in monitoring, and some very sophisticated efforts are now kind of well underway in the monitoring world to real-time model multiple data streams and update those data streams. And you mentioned, Janine, real-time geochemistry. So one of the amazing things that we saw as an innovation during the Kilauea eruption a couple of years ago was a very rapid turnaround through various labs, including, I think, the Smithsonian, to get rapid chemical data and to be able to actually use that. That's something we hadn't really had before, and it's very important. So just the speed at which we're able to do things in the modern world is really improved, and it it's quite critical when you're dealing with a situation that may be changing rapidly or you need information very quickly.
It makes it seem even more incredible that the volcanologists did what they did with the tools that they had and the knowledge that they had in the time. It's amazing, and they did save lives doing it. So
it was an incredible effort, and you know, 40 years out, I think we're all still really grateful for the efforts then, the difficult situation, the success, the personal risk, the stress and exhaustion that all of those scientists were certainly under. And this eruption, you know, stands as one of the great successes and one of the, you know, the key eruptions that really taught us a lot about how volcanoes work. So, you know, it's amazing to look back and see that, you know, how much they were able to do and understand 40 years ago, and how much we learned from those efforts.
thank you so much for joining me. I really appreciate your time.
It's my pleasure, Janine. Thank you so much.